Welcome to physics class on refraction through spherical surfaces and Lensmaker's formula. Now I will try to make these topics into two parts if possible, but if not possible then it can be also done in a combined form, okay. But if it is too lengthy, okay, while teaching this topics, then let me make it into two parts, okay. Then this refraction through spherical surfaces and Lensmaker formula, it can be part 1. That means this video will be the part 1 of this refraction through spherical surfaces and Lensmaker formula. So now let's see about the different type of spherical surfaces. I mean those spherical surfaces, refracting, I should say, refracting spherical surfaces. The first one is that of the convex spherical surfaces, and another one is what concave refracting surfaces. How it can be named? If this refracting surface, okay, bulges outward in that of the rarer medium, then we call it that refracting surface as convex refracting surface. And if it is concave toward the rarer medium, then we will call it that as what concave refracting surface. This one is concave and the first one is convex, okay. So let's see those different media here. So we are taking as two figures here. One is what with a convex, that means bulging outward toward the rarer medium. That means you can also say convex toward the rarer medium, okay. This side is a rarer medium, so we call it this as convex refracting surface, and this is concave toward the rarer medium, so it is known as what concave refracting surface. Now let's see the different points, okay, to be noted, and you can take it this line as the what are the principal axis of this spherical refracting surface. Let's name it those different points like this. This green is the pole of this concave refracting surface. Here also this green point here, this is known as the pole of this concave refracting surface, and this red point are nothing but these are the center of this spherical surface. Got it? For this concave also this one, if it had been the spherical surface like this, okay, for this concave one, then this would be the center of that spherical surface, okay. This also, if it is coming like this, the spherical part, I mean the sphere, so from that sphere we remove it this much portion, so this part, curved part, is nothing but this is a part of the spherical surface. This also like that, so that center of this spherical surface, okay, the center of the sphere out of which this part has been removed, that particular point we call it as center of this spherical surface. Now let's name it like this, A, P, C, B. This P will be for the pole, okay, and C for the center of what that spherical surface, right? So what happened from P to C, we call it that as radius of curvature. From P to C, all measurements should be started from the pole of this spherical surface, okay. So this is the radius of curvature, okay. Then what happened, your APCB, as I told you that this line is your principal axis, C is your center of curvature or center of that spherical surface, you can say, and P is the pole, R is the radius of curvature, okay. Now as I told you that if this spherical refracting surface, if it is convex toward the rarer medium, then we will call it that as what, a convex refracting surface. If it is concave toward a rarer medium, then we call it that as concave refracting surface, okay. Let's try to see what are the assumptions to be taken while taking these refraction through this spherical surface. These assumptions will be also the assumptions for Lensmaker formula, okay. At the time of Lensmaker formula, okay, the assumptions to be taken are the following assumptions that we are going to discuss it. Now the first assumption is that object is taken as the point object. Point object means it is a point size object. That means the object should be very small, lying on the principal axis, and the incident ray and the refracted ray make small angle with the principal axis. Okay, those rays which are form with these incident ray and the refracted ray, they form what small angle with the principal axis. That means the aperture of this spherical surface are assumed to be what, small. Okay, that is because of this small aperture, the angle formed by the incident ray, refracted ray, okay, with the principal axis are also small, right? Now let's see the new sign Cartesian. Okay, this sign or the sign convention or new Cartesian sign convention will be followed while taking this what, refraction through the spherical surface, and this will be also followed at a time of Lensmaker formula also. Okay, that means this sign convention will be used at the time of Lensmaker formula. Now the incident ray is taken from the left to right. Okay, that means the object is always placed at the left side and the refracting surface is always placed on the right hand side, right? Yes, all distance are measured from the pole of the refracting surface. Got it? All distance are measured from the pole of that refracting surface, and those distance measured in the direction of the incident ray are taken as positive, whereas against it will be taken as what, negative. Okay, yes, the vertical distance are measured from the principal axis. In the upward direction we will take it as positive, and if it is downward, then it will be taken as negative. So these are the assumptions and sign convention we have seen. Now let's see about the refraction, okay, at convex surface from rarer medium to denser medium and forming real image. There are various, okay, refraction that we need to discuss it, even though it is of convex surface. Okay, this is the first one, refraction at convex surface, and it is from rarer medium to denser medium. Okay, it may be of two types, forming real image, okay, and another one is forming for virtual image. Okay, forming for virtual image. Let's try to see it in these different ways. Okay, and now the first one first. Okay, so let's take it that this is the convex surface, and the refraction is from rarer to the denser. That means object should be placed at the rarer medium and refraction should take place in the denser medium, right? So let's see all the diagram one by one. So this is the rarer medium having refractive index mu1, okay, and the denser medium, this is a refracting denser medium having what, refractive index mu2. Now this is the center of curvature for this spherical surface pole here. Then we can draw the principal axis like this. Then what happened, let's take it this point O as the position of the object, and from this light from this point which is taken as the object, from this object light will start what, coming or incident onto this spherical surface. Okay, two light rays may be coming, one from here and it will take refraction, and the other will be passing here through the pole, passing through the center of curvature. Okay, so let's take it that this is the light ray, the first light ray, and this is the second light ray. Okay, when light travels from rarer to denser, it will bend toward the normal. Now if we take it that this line as the normal, okay, and AC this as a normal, okay, normal at any point. Now let's take it that this A is the incident point. Okay, A is the incident point or point of incidence we can say. So from this point of incidence to the center of curvature, that line drawn here, that will be always a normal onto this surface. Okay, so your normal here, suppose if this point of incidence is somewhere here, then that line joining from this center of curvature to the point of incidence, that will be the normal at that point of incidence, right? Yes, here also like that. So what happened, this angle between the incident ray and the normal, we call it this angle as the what, angle of incidence. Angle between the normal and the refracted ray, we call it this angle as the angle of refraction. Got it? So what happened when light travel from rarer to denser? Instead of going straight, what happened as the density are different? What happened? This light ray which is supposed to pass here, if there had been no refracting medium, then what happened? Light ray should bend toward the normal, right? When light travels from rarer to denser, we have already learned in class 10 that the refracted ray bends toward the normal, right? So it will bend, instead of going away like this, it will bend toward the normal. And another ray which is passing through this pole, then to center of curvature, then what happened? This light ray which is supposed to pass through the center of curvature will go without any bending or deviation. So it will pass here like this. These two refracted rays, one is this one is refracted ray, another is this one. So the two refracted meet here, and this will be the point of the position of the image. Okay, the image will be formed here. So the angle between the incident ray and the normal, we call it as angle of incidence. The angle formed between that of the refracted ray and the normal, we call it that as angle of refraction. Okay, so what happened from this point of incidence? If you draw a perpendicular onto the principal axis, that means AM, if you draw it perpendicular, then what happened? For any calculation, we will take it, say suppose if you are taking this right triangle like this, AMO like that, but these, as this aperture is small, then what happened? The measurement from M to O, for example, if you want to take it that of your object distance, then it should be measured from pole. The distance between from P to O, we call it that distance as what? Object distance. But for our calculation, we will start it from M, okay, because this is the right triangle. So whenever we require it, then this distance, I mean P and M are very close to each other. So whatever the measurement we measure it at the object distance PO, that will be also approximately equal to MO. Okay, so this distance PM, that is negligible. Got it? Now let's see the angle formed by the object. We call it that as what? This as taken as alpha. We use the symbol for object. Okay, keep in mind that for the incident ray that forms with the what? Principal axis, that means the incident ray will be coming out always from the object. Okay, for the object, that means incident ray and the principal axis, the angle formed between them will be taken as alpha. And for that of the incident ray, I mean refracted ray and the principal axis, that angle will be called as what? Beta. Don't forget it, alpha, beta, gamma. That means object, image, radius of curvature. Don't forget it this. For object, we will take it as alpha. For image, it will be taken as beta. For that, what? Normal, or rather the center of curvature, we will take it this as gamma. Okay, so for object means it will be incident ray. For image means it will be the refracted ray. For center of curvature means it will be always the normal. I am repeating again, the angle formed by the incident ray with the principal axis, that will be taken as alpha. Clear? And for that of the angle between the refracted ray and the principal axis, that angle will be called as beta. The angle between the normal at the center of curvature, I mean, with the principal axis, that angle here will be called as what? Gamma. Got it? Like this. Clear? So we need to take it that, okay, some assumption here also, that this, we know that in a triangle, okay, if you take it this triangle, for example, that triangle, which one? Here is your angle, a triangle, we can take it from here, triangle OAC. This is a triangle, right? For this triangle OAC, what happened? Your angle I here, this angle I is the exterior angle. We know that in geometry, that exterior angle is equal to sum of the interior opposite angles, right? So we need to use that one. And as I have said that this in the assumption, we have said that this angle formed by the incident ray, the refracted ray, and the normal, as they are small, assumed to be small, then the tangent of these alpha will be approximately equal to what? Alpha. Tangent of beta will be also approximately equal to beta. And this sine of angle, if angle theta, let me write it here, okay. If theta is small, okay, if theta is very small, then what happened? Tangent of theta will be also approximately equal to theta. Similarly, like that, sine of theta will be also equal to what? Theta. So for our what purpose, whenever required, we may either use tangent of theta or sine of theta. Got it? That can be done. Now let's see. See, this is the radius of curvature, and the object distance means P to O is the object distance denoted by U, and from P to I, that will be the image distance. Image distance means distance from the pole up to the image, that we call it as image distance denoted by V. Now let's see the geometry that I have told you, that in the case of that what triangle, suppose if it is a triangle like this, and if you produce it this line, then we call it this as the exterior angle. Okay, let's take it that this is I, as similar to triangle OAC. Okay, this is OAC like this. So the interior opposite angle, are what? This one is what? Alpha, right? And this one is what? Gamma. Got it? So exterior angle of this angle, okay, inside a triangle, so we call it this angle I as the exterior angle of this A. Got it? Exterior angle of this A is what? I. So angle I will be equal to, exterior angle I will be equal to sum of the interior opposite. These are the opposite and also inside the triangle itself. So we call it this alpha and what? Gamma as the interior opposite angle. So we know that exterior angle of a triangle will be always equal to the sum of the interior opposite angle. That is what we are having here in this, the first one, alpha, okay, plus gamma will be equal to I. What is I? I is nothing but this is the angle of incidence, and angle of incidence is equal to alpha plus your gamma. Similar to that, like this in the triangle. So what is this? The first triangle that we have taken, the first triangle as that containing object. Next, in the next triangle, you need to take it which contain this image. This will be always there, whether it will be refraction for any mode of what refraction, whether it may be refraction for convex surface, rarer to denser, forming for real image or virtual image, or whether it may be concave surface, okay, rarer to denser medium, whatnot. There are different type of refractions that we are going to discuss it, and it will be following the same steps. Got it? The first one is what? You need to take it that right triangle containing this object, not right triangle, any triangle containing this object, so as to take it that exterior angle is equal to sum of the interior opposite angles. Okay, so in that first triangle, what we have taken is from where? This is from triangle what? OAC. Okay, O is there, that means containing object. Now let's try to take it for the second triangle containing what? Your image. Let me pull it somewhere here. Okay, it gives problem. So what happened? Let's take it for that of your what? The second triangle containing this image. Okay, this image. So it will be what? Triangle IAC. So in that triangle IAC, that triangle is where? This is IAC, this triangle. Okay, and your gamma will be the exterior angle for this triangle. Okay, so your gamma will be equal to what? R plus beta, interior opposite angle here and here. Got it? So this is the exterior angle, and these two are the what, interior opposite angles. So your gamma will be equal to what, r plus beta, right? Yes. Now let's see then what happened. We need to express it. Okay, don't forget this. We need to express it, one for angle of incidence, one for angle of incidence, okay, and another one for that of your what, r. So we will try to express from this second equation r as what, gamma minus beta. Got it? Then what happened, let's try to take it, okay, this alpha will try to express in terms of that perpendicular and that of this. So from this right triangle OAM, okay, if we take it tangent of alpha, then tangent of alpha will be equal to what, perpendicular means AM and base will be OM. Okay, so OM and what, your PO, we will take it, or rather you can take it MO. Okay, so your alpha will be equal to what, AM by MO, and this AM by MO we can replace it by PO also, that instead of MO we can replace it by PO. Let's see the next by step. Says, see, tangent of alpha will be equal to MA divided by MO, and this can be, okay, related as what, alpha is equal to MA by PO. Okay, why? Because alpha is very small, so if it is, this angle is small, then tangent of that small angle will be approximately equal to the angle itself. Okay, now let's see for that of beta gamma also similarly like that. Okay, this is the first one is triangle from triangle OAM, right triangle. For this triangle what containing this beta will be what, triangle what, AMI. This is for the containing the image, okay, this one. So what, in the right triangle AMI, what happened, tangent of beta will be what, AM by MI, right? So your beta will be equal to what, MA by MI. Likewise your tangent of gamma will be equal to what, your AM by MC. Okay, so instead of here mm here in this denominator, we will replace it by what, p in the next step, subsequent steps. Okay, it will be coming like that. Now let's see, let's try to find it out for the sine of angle of incidence to the sine of angle of refraction. That means your Snell's law, that is what, okay, in that laws of refraction I told you that we have already done that. This sine of angle of incidence to the sine of angle of refraction, this is always bears a constant, and that constant we call it as refractive index of the second medium with respect to the first, and it can be written as mu2 by mu1 like that, no? So similar to this, what happened, your angle of incidence and angle of refraction are also small, so we can write it as what, I by r is equal to what, mu2 by mu1. As I told you that if alpha or angle is small, then that sine of that angle will be approximately equal to the angle itself. Similar likewise in the case of tan also. Okay, so tangent of that angle will be approximately equal to the angle itself. If that angle is very small, then we can express it as mu1i is equal to what, mu2r. Okay, like this. So then what we are going to express is that instead of this I, we need to replace it by that alpha plus gamma. Instead of r, we need to replace it by what? Instead of this angle of refraction, we need to replace it by gamma minus beta here. Okay, then let's see, the equation will be coming like this. I told you that MO, MI, MC will be replaced by what? PO. Instead of MO, we can take it by PO. Why we are doing like this? Because any measurement okay, parallel to the principal axis should always be started from the pole. This is the what? Convention. Got it? Convention means already accepted by many of the scientists, okay, all over the world, by almost all the scientists over the world. Okay, and for that of mi, that means for your image distance, it will be replaced by pi. So if you replace it, those m here by p, then it will be equal to what? Po. This one will be also pi, this will be also pc, like that. Got it? So after substituting those values and after rearranging it, then it will be coming up like this. Got it? Mu1 by I means what? I means this one alpha plus gamma. So alpha is what? Ma by Po, right? So from where this Ma has been removed, because in all the terms in the numerator Ma will be all there. So you can cancel it, those things, and you will get it like this. So after putting the sign convention, okay, for PO, this is against the incident ray. Incident ray is in this direction from left to right, and if you are going to measure the distance of the object, okay, from the pole, then you need to measure it in this direction. This will be 0, 1, 2, 3, like that. That means your measurement is against the incident direction. So what happened? Your measurement of the object, rather your object distance PO, will be considered as or assumed or taken as negative, and object distance is denoted by U, so it will be mu1 divided by minus U. It will be coming up in that way. Got it? After putting all those sign convention, then it will be coming like this. So what happened? I will tell you one mnemonic for this, okay, and it will be used, these mnemonics, all over the refraction that we are going to discuss now. Got it? The first is what? You try to think that your refraction is from rarer to denser. Okay, this is your rarer medium, this side I mean, and of whose refractive index is what? Mu1. Okay, and it goes to that of the denser medium to what? This having refractive index mu2, like this. So first you need to take it like this, that you take the refractive index from where the light goes first. Okay, it was going from mu1, okay, to mu2, like this. So you divide this refractive index of the first medium by what? Minus of the object distance. Okay, let me write it first with a different color. Okay, that will be better. So let's take it that I told you that the refraction is from mu1 to mu2. So you divide this mu1 by minus of the object distance, then it will be what? Plus second medium refractive index divided by the image distance. Okay, then this will be equal to what? You take it this mu2 first here, mu2 minus mu1 divided by its radius of curvature. This will be always there like this. Got it? The first is what? The measurement, the light is, or the refraction is from mu1 to mu2. You remember in this way. So you first write it this mu1 first, divided by negative of the object distance. Then what happened? You divide the refractive index of the second medium by its image distance. Okay, and then you take it the opposite of this, from u2 to u1 in this way. But here again there will be minus. Okay, in the numerator it will be mu2 minus mu1 divided by the radius of curvature, like this. Can you get my point? Yes, I think it is very easy. Let me repeat it again. Okay, because it is very important, that's why I am just repeating it. Okay, for those of the different type of refraction, I will not do all like this. Got it? We have to take the similarity or analogy, then we have to write it for those different type of the refracting surface forming different images, whether it may be real or virtual. I am telling you that the refraction is from mu1 to mu2. That means from rarer to what? Denser medium having refractive index mu1 to mu2. You think it in that way, mu1 to mu2. So you divide this refractive index from where it starts to from where it ends, divided by what? Its object distance. Object distance, for object distance you take it minus of the object distance u, and plus the refractive index of the second medium divided by its image distance, and this will be what? The ratio of what and what? Difference of the refractive index to the radius of curvature. So while taking for this one on the right hand side, you need to think that it is coming back again from mu2 to mu1 like this. You write the refractive index of the second medium mu2 first, then minus mu1, then you take it the radius of curvature in the denominator like this. That is what it is written here also, okay, here, clear in this, right? Yes, let's see in the next part, okay, that is for refraction at convex surface. Now this is from rarer medium to denser medium still, but the image will be now virtual, not real image. Now what I want to tell you for that in the previous one, this one for forming real image, okay, for forming real image, don't forget that this object should be little bit far away from the pole. If this object is very close to the pole somewhere here like this, then it will surely form what? Your virtual image. Got it? So virtual image should be brought closer toward the pole. Okay, you must be remembering the image formation by convex lens in your class 10. Okay, when the object is beyond its center of curvature, then what happen? Your image will be what? If your object is beyond the focus, then the image will be what? Real, right? If the object is placed within the focus, that means between the pole or center of curvature and that of the focus, then the image will be what? Virtual. Likewise here also what happened? The object to be placed should be what? It should be near the pole. Okay, so let's see the diagram here. This is the diagram. Okay, let me zoom in so that you can see it very easily. Now I told you that this is the pole. Okay, whatever that we have drawn, it is same thing. Okay, rarer to denser medium having mu1 to mu2. Okay, now see the object is placed closer to the pole, not far away. Got it? Then what happened? From this object, light ray will be coming like this, one light ray, and this will be the point of the incidence onto this interface, right? Then what happened? The normal at the point of incidence, I told you that the normal at the point of incidence will always pass through the center of curvature. So angle between the normal and the incident ray, we call it that as the angle of incidence. This will be the direction of the actual incident ray, okay? But see, as the light ray is traveling from rarer to denser, what happened? It will bend toward the normal, right? Instead of moving like this, the refracted ray, it will bend toward the normal. Got it? And this is the refracted ray. Got it? The refracted ray seems to be coming out from somewhere here. If you retrace backward, okay, this, if you draw backward like this, then this will be the point where this refracted ray seems to be coming out from this principal axis, okay? And another ray from the same object, it passed through the pole and goes to the center of curvature, so it goes without any bending. So this refracted ray here, PC, okay, this seems to be also coming out from somewhere here like this. So the two virtual refracted ray meet here at this point I, and this I will be the position of the image for this object at O. Got it? Similar to that previous one that I have told you that this angle of reflection, incidence, incident ray and the normal, we call it that angle as angle of incidence, angle of refraction, the refracted ray and the normal. I told you that alpha is the angle formed by the incident ray with the principal axis, beta is the angle formed by the refracted ray and the principal axis, gamma is that formed by the normal with the principal axis. Alpha, beta, gamma, object, image, radius of curvature. Okay, so we have all done this one. So what happened? the same logic or the same mnemonic will be used here. So let me write it that one here. Okay, refraction is from where to where? From rarer medium to what? Denser medium, right? Having what? Refractive index mu1 and mu2. So I told you that you need to write it this mu1 divided by minus of its object distance u, plus this will be, okay, divided by the image distance, and your image distance is v here. Okay, don't worry that this is against the incident ray. After taking all those sign conventions, that whatever we have done in the previous case, okay, it will be coming, all those, after putting those sign convention, it will be surely coming with that of v only, image distance, and this will be equal to, now you need to think that it should be returning backward from mu2 to mu1. So you need to write it mu2 first minus mu1, and this will be the radius of curvature. This formula will be always there, as I said. Okay, if you take it that mnemonic, whatever I have said, okay, if you follow it, then it will be coming like this. So let's see in the next step. See, this is the thing that we are going to do it. If you want to do it, then I can do it, but it will take long time. Okay, so instead of that, you try to do it. If you have a problem, then you just ask me later on, okay, after watching this video, okay, and I will show you, okay, or rather I can make you another video for all those, these different type of observations, okay, for different types of refraction, I should say. Similarly, like this for other type of the refraction, okay, refraction at concave surface from rarer to denser medium. That means it will be what? It will be in this shape. See here, it is concave toward the rarer medium, and it is always forming the virtual. In this case, what happened? There will not be no real image formation. Okay, it will be always virtual. So for this also, if you take it the same thing, it will be having the same rule. Okay, this is for mu1 to mu2. Okay, your mu1 minus u, okay, mu2 divided by v, that will be equal to what? Mu2 minus mu1 divided by its radius of curvature. Got it? It will be here coming like this, the same relation. Okay, so whether it is real or virtual, it is immaterial. The same what mnemonic that I have told you, it will be followed. Okay, yes, let's see for the other refraction at convex surface from denser to rarer medium. Now this is the diagram that we are going to have. Now you see that this is refraction from denser to rarer. From denser, that means mu2 to mu1, okay, and it is convex toward the rarer medium. That is why we call it as convex surface. And this is forming for real image. Okay, for forming real image, I told you that object should be somewhat farther away from the center of curvature. It should be beyond center of curvature, and so the image will be formed there as real. For this, what happened? You need to take it that this is for what? From denser medium mu2 to mu1. You write it like this. So the object distance will be minus u, okay, and this will be what? Image distance plus sign will be there, and this will be equal to what? Mu1 minus mu2, and you need to take it your radius of curvature like this. It will be coming in this way. Okay, in this way. Got it? For this one, let's see what it is written there. Okay, see, it is equal to what? From mu2 to mu1, so divided by object distance plus mu1 divided by image distance, and you need to take it mu1 minus mu2 by its radius of curvature. Same is the case in the case of what? Forming virtual image. Okay, in this case, what happened? The diagram is not drawn here, so for you I have to draw it here again. This is for what? Convex. So your convex surface will be here like this, and we have to think that the first medium is almost all denser medium having your refractive index mu2. Okay, you need to take it that this is the principal axis, and for forming what? Your virtual image, your what object must be somewhat closer to here. So let's take it closer to the pole. So we need to have it this as the object. And what happened if we make it that this is why it is coming up as curve? Let me draw it again. Okay, or rather I will draw it from here. So this is the convex surface having refractive index mu2, and this side is the rarer medium having refractive index mu1. Okay, now this is the principal axis. Let's take it pole here, and we need to take it the object here like this at O. Okay, and so what happened, this is the incident ray, so this angle will be what, your angle alpha, I mean this angle here. Got it? Now what happened, as the refraction is from denser medium to rarer medium, it will bend what, your center of curvature, it is somewhere here, so the normal will be the line like this. So as the incident ray, actual incident ray will be in this direction, in this way. So what happened, as light travel from denser medium to rarer medium, it bends away from normal, right? So it will not, instead of bending this incident refracted ray here, it will bend away from here like this. It will bend in this direction. Got it? So if it is bent in that way, then what happened, your image will be coming here. So instead of doing like this, let me take you, okay, in a new screen like this, it will be better. Let me draw it in a very magnified way like this. So this will be the convex surface toward the rarer medium, and this is a denser medium, okay, having refractive index mu2, and the refraction is from rarer to denser, I mean denser to rarer. So this is your denser medium and this is your rarer medium. Okay, so your principal axis is somewhere here like this. This is the pole. Okay, and let's take it that your center of curvature is here like this, right? So let's take it your object somewhere here, and the object max, okay, incident onto this. So this is the incident ray, and the normal will be passing a line. This is the point of incidence, we can call it as A. So from C to A we need to draw it that normal like this. Got it? So your incident, actual incident ray is here like this. Got it? So instead of this, what happened, the refracted ray should what, bend away from normal. Why? Because it is from denser to rarer. So instead of going here like this, it will be bended in this way. So this will be the direction of the refracted ray, and this refracted ray seems to be coming out from somewhere here. Got it? Another ray which is passing here, okay, it will go without any bending. So this refracted ray seems to be coming out from somewhere here. So the two refracted, virtual refracted ray meet here at this point I like this. So the angle formed by the incident ray and the principal axis, we call it as alpha. The angle formed by the refracted ray here and the principal axis here, we call it that as beta. The angle formed by the radius of curvature here with the principal axis, we call it that as gamma. The angle formed by the incident ray with the normal here, this angle we call it as what, angle of incidence denoted by I. Angle formed by the refracted ray here with the normal here, this angle we call it as what, angle of refraction. Okay, like this you need to find it out as we have done. First I told you that you need to take it that triangle containing what, object. So when you take it that triangle containing the object, then it will be equal to what, this triangle you can take it, okay, triangle OCA. Can you get the diagram here, OCA? Okay, so if you take it that triangle OC, then A, it will be like this. Okay, this angle is what, alpha, this angle is I, this angle is what, gamma. Okay, so your alpha will be equal to I plus gamma, we can write like that. So we need to express it this as I is equal to what, alpha minus gamma, like that. So starting from there, if you continue it as we have done, then you can easily get that expression. Okay, what expression? The expression that we have done. that refractive index mu2 divided by its object distance. Okay, this will be the object distance. So the mnemonic that we use is what? Mu1. We started from the refraction mu2 to mu1, from mu2 to mu1. Okay, from mu2 to mu1, right? So your mu2 to mu1 divided by object distance minus of object distance, this is the object distance, got it, plus mu1 divided by its image distance. Don't think that it is against the incident ray. After taking all those things, sign convention and all, it will be coming only what? This will be V. This will be equal to what? Your mu1 minus mu2 divided by R. That will be the formula for this type of refraction, from denser to rarer, convex toward the rarer medium, forming what? Virtual image. Got it? So let me take you onto that slide again after erasing this. Okay, and that is what we have done. So that will be the diagram as I have drawn. Okay, let's erase it. Okay, I will not draw it again, otherwise it will take long time. Okay, yes, the refraction is also coming like that for that of the convex surface. Okay, this one for the convex for the concave surface, for the convex surface we have done. For the concave surface also you can do it for the refraction from denser medium to rarer medium. In that diagram it will be like this. Okay, let me draw it. For forming what? Virtual image. So it will be concave like this, and this side is denser medium. Got it? Like this. So this is your pole, this is your mu2, and this side will be what? Your mu1. Okay, like this. So this is the pole, this point I mean. So your center of curvature will be somewhere there. Got it? And let's take it that object is somewhere here. For this one, if you take it like this also, it will always form the virtual. Okay, if the object is far away or very close to the pole, doesn't matter. If you take it somewhere here also, it will form virtual image. If it is formed here, object is also here, it will form virtual image in this case. Okay, but you take it little bit far away like this so that it can be seen very easily. So your incident ray will be here like this. So this will be your alpha. Okay, and your normal will be passing through this point. This point will be nothing but this will be your point of incidence, just like this A here. Okay, so this will be your point of incidence. So let me write it here, and the line passing through this point of incidence with the principal axis, I mean with the center of curvature, that will be the normal. Okay, so angle between the incident ray and the normal, we call it as angle of incidence, right? So as the light travel from denser medium to rarer medium, it will bend what? Toward the what? It will bend, no, it will bend away from the normal. Why? Because if it is for the refraction from denser to rarer, from denser to rarer. Okay, it will bend away from a normal. So this is a normal side, so it will bend away from a normal. So instead of bending like this, it will bend away from normal like this. Okay, away from normal. So whatever the refracted ray, it goes here, the angle between the normal and the refracted ray, this angle we call it as angle of refraction. So these light ray, refracted ray, seems to be coming out from somewhere here on the principal axis. Okay, another ray which passes through the pole to the center of curvature, it goes without like this any bending, straight onto the principal axis. So this refracted ray also seems to be coming out from this point somewhere here like this. So your image will be formed here. Okay, so this will be your beta, this will be your gamma here. Got it? So after doing as we have done, similarly you will get the same expression like this. What is this? Object distance O is here. So your object distance is this one, U. This will be your image distance. That means distance between the pole and the image here. So these two, this is what? pole and this is your image. So the distance here, it will be what? Distance here, it will be your image distance. Center of curvature is here, so the distance between this pole and the center of curvature, we call it that as radius of curvature. So after using all those things, okay, that we have done, the same expression will be coming in this way again. Got it? Yes. So let's try to wind it up with that one, but these are the things that I have already told you. Okay, if you want to watch it, then pause this video and you can watch it. Okay, this one I have already explained to you, right? So with that, we will try to end this today's class, and in the next class I will try to show you about the lens maker formula in the part number 2, okay, of this.